How's everyone doing today? Are you awake? Getting in the middle of the afternoon? All right. So yes, as I mentioned, I am interested in studying in particular the impact of UV on characterizing exoplanets. And a lot of my research comes down to this question of, are we alone in the universe? I'm really interested in, can we detect life in the universe? And keep in mind, I'm not talking in this talk about intelligent life. I'm only talking about things like microbes, single-celled organisms that hopefully we will be able to detect by looking for molecular fingerprints of biosignatures in the atmosphere of these planets. And we've already heard a lot of this from David Catlin's talks earlier and other ones today. So this comes to the question of what's a biosignature. And the strongest biosignature, one of the strongest, is the combination of an oxidizing and a reducing gas together. On Earth, that's something like oxygen and ozone in combination with methane. And this is because you could get abiotic oxygen through the photolysis of water or CO2 and the loss of hydrogen, as we already heard today, or methane from volcanoes. And so again, it comes back to this combination of gases that's important, and understanding if we're actually seeing a true biosignature or not. So one thing that I want you to take away is that biosignatures really require context. They require things like knowing the surface temperature, whether it's a rocky planet, whether it has CO2 and water. And CO2 and water by themselves are not biosignatures, but they are useful for us to understand whether the planet has conditions that are conducive to life and have greenhouse gas and habitability and are useful for food, for microbes. Other biosignatures are things like nitrous oxide, methyl chloride, and dimethyl sulfide. And these are uniquely maybe biosignatures because they don't have any known abiotic sources. So sometimes we would think of these as maybe being, if we see those in the atmosphere of an exoplanet, they might indicate life by themselves. But we want to try to find these biosignatures around other stars. And I love this pale blue dot image, as we all know and love in astronomy, because if an alien astronomer were looking at Earth, they would be able to see these signs of life in our atmosphere by looking for things like methane in combination with oxygen and ozone. And we have a vegetation red edge. And so hopefully we'll get the first hint of these by being able to characterize Earth-like extrasolar planets with things like the James Webb Space Telescope and large ground-based observatories in the next decade. And so for my research, I'm really interested in this question of how does the star impact the atmosphere, spectral features, and biosignatures that we might see. So I'm going to talk a lot about various types of stars, hot stars and cool stars, and not these kinds of hot stars and cool stars, but more the FGKM ones that we're all familiar with. And when we go from F to M stars, we're really thinking of high UV to low UV environments, broadly speaking. And UV is really important in our understanding of biosignatures because UV can destroy some biosignatures, such as methane, making them maybe less abundant in the atmosphere around an environment with high amounts of UV. But it also produces, of course, other biosignatures, such as ozone, which is the photolytic product of oxygen. And so UV also, it's not just the amount of UV, but the balance between the far UV and near UV that matters. And this is in part due to, we can see this in the Chapman reactions which produce ozone, because you have certain reactions which need really the far UV and other ones which can go forward with just near UV. And so it's not just enough to know like what's the bulk UV coming in, but also the balance between the full characterization of that UV radiation field. And so I do modeling of atmospheres, and to do that I'm going to talk a little bit about how I go about this. We take an input stellar spectrum, and then I'm going to put this into a climate code and calculate, which assumes a fixed chemistry and then calculates a temperature pressure profile. And then you can feed that into a photochemical code, which using that temperature pressure profile calculates the reaction rates and updates the abundances of those species. You iterate back and forth between these two codes until you get a stable atmosphere solution. The output of this, so that's like the atmosphere part of the code. The output of this then can go into a line-by-line radiative transfer model, which will get you the remotely detectable spectra that we hope to someday observe for these planets. And so, though I've done a lot of work on also FGK stars today, just in the interest of time, I'm going to focus on M stars because they're very exciting. And M stars, we know, are also really timely because 1 in 4 M stars are thought to have a habitable planet. And of course, they're the most abundant stars in the universe, as well as they're going to have the small star advantage for our first observations. But as we also have already heard today, M stars have other problems with them. They remain active for very long periods of time and have strong flares. So modeling planets around M stars does come with some problems. When I first studied M stars, I was a little surprised when I saw this figure, because here's the M subspectral types, so ranging from M0 stars to M7 stars, and the active lifetime. And you can see here that even the early M stars are already active for much longer than a G star. They're active for 1 to 2 billion years. But then as you flip into the later M stars, they're remaining active for 6 to 8 billion years. That's a really long time. And so we have to think of, when we do atmospheric modeling of exoplanets, we need to really know kind of what type of activity we're dealing with. And so here's this little cartoon image where I'm going to just talk about some of the broad categories that I deal with in my atmospheric models. So one is an active type star. That's something like 80 Leo, a young, bright, flaring M star, the brightest and flaring star that you can get. But then the inactive model would be something like this, and that's just a Phoenix model. So just a photosphere, no chromospheric emission, and we don't actually know of any stars that are that inactive, because when we see stars that are quiescent, they're typically classified as quiescent. They look something more like this. So they have H-alpha in absorption, but they still have quite a bit of chromospheric emission. But the one key thing that we really need to figure out here is we don't actually know for what the floor of the UV flux is. We don't know, while we know some of the emission peaks, we haven't yet been able to detect and push to the lowest boundary of what the continuum is between these emission peaks. So that means, is the continuum really, is it here? Is it down all the way to the photosphere? We actually don't know yet, and I think it's a vital thing that we need to learn about in the next few years, especially while we have Hubble, in order to better understand what's happening in the atmospheres of planets orbiting M stars. So I think modeling with real UV is very important, and this is the same figure as before, only now with real stars. So this is, like I said, 80 Leo, a quiescent star, and the red is just the Phoenix model, and you can see here that there's 10 orders of magnitude if you were to just naively not assume a real UV star in your model. So this is why we need to have observations of the UV of the host star. And I wanted to show this also just on a linear scale, because what we're really talking about is just this part of the flux. And it doesn't seem like that UV would be, it's not that big of a fraction of the total flux, but it's really what's driving all the atmospheric chemistry and our understanding of what's ultimately going to be in the atmosphere. And so let's look at some planet direct detection IR spectra. And here you can see, I'm just going to show kind of the extreme cases, and just for a few of them. So this is an M0 and an M9 for the active stellar models. This is for the minimum possible UV. And then for the muscle stars, these 6 typically classified quiescent stars, and looking for an Earth-like planet and just changing it around these different stars. So the first thing that pops out at you is some of these features could change dramatically depending on how much UV you have. And even for the Hubble stars, you start to see this dip in the 18 micron feature for N2O. And so knowing what the UV level is and how low UV could be around these M stars and for cool stars, I think is really going to be important for us to try to see if we can detect biosignatures. Obviously, UV also impacts things like methane and of course ozone, because ozone is produced by UV. So what I want to show you is just kind of an example between the two extremes. So this is an Earth-like planet orbiting the same stellar effective temperature, but just with the minimum and maximum UV. And so here's that case where you have the black line is a young flaring star, and then this would be the lowest possible UV that you might expect. And you can see that the features change quite a bit just based on what's created and destroyed in the atmosphere of those planets. Keep in mind that this red model is probably lower than what we would actually expect for real stars, because real stars probably don't have that low of UV. But this leads into one of the projects that I was talking about on Monday. We found these planets around the TRAPPIST system, And so one of the things that we want to do is when we start thinking about even cooler stars is how are we going to get the UV for that? Because right now we don't have observations of characterizing the UV of brown dwarfs. And so maybe scaling down some of these later M stars or scaling up UV from Jupiter Aurora, because we've already last year detected aurora around some brown dwarfs. So the second thing that I wanted to, I just want to summarize this part of it with the stellar type really matters, the UV really matters, and I hope I've convinced you of that. So the thing that I wanted to talk about just briefly before the end of this talk is that planets change. We've also heard this today with David's talk. We have planet evolution from geology, plate tectonics, and life. These things are all intertwined, like Colin nicely stated at the end of his talk. And we've also already seen this figure of the Earth's kind of general atmospheric state over time. So here you have time in billions of years, and these concentrations, we maybe had more CO2 at the beginning, the rise of methanogenesis, and then, of course, the rise of oxygen here in maybe 2 different steps. And so I'm going to show in the next few slides here 4 types of atmospheres. Something that's a prebiotic atmosphere, a 1% oxygen concentration, 1% of modern, so that would be 0.021, and then 10% of modern concentrations, and then modern Earth type atmosphere around different types of stars. And so this is that figure. So here on the top is the prebiotic case with these FGKM stars that I told you about before. And then this would be the 1% of modern concentrations, 10%, and finally the modern atmosphere. What we first, of course, obviously jumps out is the ozone feature. As we would expect, as oxygen rises, we start to see the formation of ozone. And for F stars, this happens very early, right when you don't need that much oxygen to get quite a substantial ozone shield in Earth's history. And in fact, it's even stronger here for these 1% and 10% than it is at modern oxygen concentrations for the F stars. Another thing that we really want to maybe detect, going back to this idea that biosignature is the combination of an oxidizing and reducing gas, we would love to be able to see something like methane and ozone in combination in the future to see if we're seeing life. As well, the carbon dioxide feature, that central emission peak can be a secondary indicator of a thermal inversion in the atmosphere and can also be useful for us to detect. So looking at the oxygen feature in the visible, so this is now just one feature, not the whole spectrum, but for the same 4 cases, you can see for the clear sky case, you get the little dip here and then a bigger dip, and of course the nice big oxygen feature. But when we move that to consider 60% clouds, you can see, so this is 0%, and then you have 1% of modern concentrations, it really diminishes that feature. And I showed a different plot when I was explaining some of the projects on Monday. This as well, when you have 10% oxygen, you get a kind of nice feature, and clouds really diminish it, but the effect isn't so strong for the modern atmosphere. And so the situation is different for ozone, though, because ozone's in the IR, and the features behave a little differently. And so here you can see this is the clear sky for these 4 epochs for the different star types and the 60% clouds. And there's not, comparing the two, there's not so great of a difference like you saw in the visible part of the spectrum. So comparing those two together, our detectability of oxygen versus ozone through time, ozone would pop out much quicker in Earth's history, if a planet's following Earth's history, than oxygen, just because of the clouds. And all solar system planets do have clouds. So that tied into one of the projects I was thinking a student might be interested in, is looking at a more wider range of cloud parameters and properties, and seeing if we can hammer down exactly how the detectability of oxygen is going to be impacted. So in summary, UV really dominates the atmosphere and the spectra of extrasolar planets. To know the planet, we really need to know the star UV. I think we're learning that more and more in a lot of different situations here. Clouds for oxygen is maybe going to make it much more difficult for us to detect, but for ozone, it's not so much of a problem. On my website, there's some products and tools you might find interesting. You can, of course, talk to me about them while we're here. I have a high-resolution planet spectral database going from visible to IR for 27 different stellar types and 4 different geological epochs for all these planets, so a nice big grid of kind of a range of planets that you might want to look at, as well as high-resolution input stellar spectrum with accurate UV modeling and observations from Hubble and the International IUE. Please feel free to come and chat with me about any of these things. I love talking about all of them. And with that, I'll take questions. Thank you. Let's go. Yeah. So I think that's, so that paper is from West 2008, and that's looking at, in particular, H-alpha and emission, which they have, they averaged up each subspectral type within the M spectral class, because that's how M stars are typically classified as active or not. So if the H-alpha is an emission, and yeah, yeah, yeah. I'd have to go back and look at the West 2008 paper. I know he's also written stuff on the rotation rates as well. I think just recently with Zach Berta on rotation rates and activity and lifetimes of M stars. But with this database, I know it was like taking H-alpha measurements and looking at the fraction of these planets or stars that are observed to be active or inactive. And they had about like 2,000 or something that they average. Yeah, yeah. So we were talking a lot about it today with David Catling, but so basically when we're thinking about an atmosphere, with the climate code, you have the radiation coming in on the top of the atmosphere. You have heating by water and carbon dioxide and ozone, and then that really sets, your relations for the climate profile, like these bulk greenhouse gases. So that's where you start, and then you take that to then feed into a photochemical model and use those temperatures and pressures to see what the reaction rates are. That feeds back into the climate. Does that change? Do you get, more greenhouse gas, and then you would have additional warming, stuff like that. Yeah.
Can you talk a bit more about why the ozone is stronger?
Yeah, that's a very interesting point, and it's been pointed out by Frank Celsis actually over a decade ago, in that it kind of washes out its own feature. And so what happens is the hot stratosphere. So if you think, so I didn't show this plot, but basically F stars have a much hotter stratosphere because of that additional ozone. So the ozone heats up that stratosphere, and then the temperature difference between the stratosphere and the surface isn't that great. And so in the IR, it's also the difference between the surface, where the surface is emitting as a black body, and then where the temperature of the layer that's doing that you're seeing the feature from, that temperature difference really matters in addition to the abundance. So in the visible spectrum, it's just the abundance of a gas that determines this feature depth, whereas in the IR, it's the temperature difference. And so as you heat up the stratosphere, it makes that temperature difference decrease, and therefore it washes out that feature. And so in fact, for the hottest F stars, you actually start to see the ozone feature go into emission because of that. So that's basically why. So it is interesting, as well as some other spectral types for modern Earth have stronger ozone features, like the K stars have a stronger ozone feature, even though they have less ozone, but because the temperature difference is greater. So it's not, it's a little less intuitive, and that's also why clouds are not quite as intuitive either, because it relates back to these temperature differences. Some of them. We don't know the floor. We know some of them. Yeah, so I think it does, because I haven't done a full sensitivity test where I've tried different amounts, but I did do one where I just only increase Lyman alpha because everyone is like, oh, Lyman alpha is the only thing that matters for M stars, but that's not true. So you can take Lyman alpha and multiply it even by like 1,000,000 times or 1,000,000,000 times, and it actually doesn't change what's happening in the atmosphere. So that's why I would think that the continuum really matters. And so for some stars, we have measured the continuum, but other stars we haven't measured the continuum. And I think that's something that is important for us to do going forward. Yeah. Okay, thanks. All right, I think that's it. I think I'm done. I think they're kicking me off stage now. Thank you. The organisms that hopefully we will be able to detect by looking for molecular fingerprints of biosignatures in the atmosphere of these planets. And we've already heard a lot of this from David Catlin's talks earlier and other ones today. So this comes to the question of what's a biosignature. And the strongest biosignature, one of the strongest, is the combination of an oxidizing and a reducing gas together. On Earth, that's something like oxygen and ozone in combination with methane. And this is because you could get abiotic oxygen through the photolysis of water or CO2 and the loss of hydrogen, as we already heard today, or methane from volcanoes. Biosignatures are things like nitrous oxide, methyl chloride, and dimethyl sulfide. And these are uniquely maybe biosignatures because they don't have any known abiotic sources. So sometimes we would think of these as maybe being, if we see those in the atmosphere of an exoplanet, they might indicate life by themselves. But we want to try to find these biosignatures around other stars. And I love this pale blue dot image, as we all know and love in astronomy, because if an alien astronomer were looking at Earth, they would be able to see these signs of life in our atmosphere by looking for things like methane. And so again, it comes back to this combination of gases that's important and understanding if we're actually seeing a true biosignature or not. So one thing that I want you to take away is that biosignatures really require context. They require things like knowing the surface temperature, whether it's a rocky planet, whether it has CO2 and water. And CO2 and water by themselves are not biosignatures, but they are useful for us to understand whether the planet has conditions that are conducive to life and have greenhouse gas and habitability and are useful for food, for microbes. Other in combination with oxygen and ozone, and we have a vegetation red edge. And so hopefully we'll get the first hint of these by being able to characterize Earth-like extrasolar planets with things like the James Webb Space Telescope and large ground-based observatories in the next decade. And so for my research, I'm really interested in this question of how does the star impact the atmosphere, spectral features, and biosignatures that we might see. So I'm going to talk a lot about various types of stars, hot stars and cool stars, and not these kinds of hot stars and cool stars, but more the FGKM ones. So how's everyone doing today? Are you awake? Getting in the middle of the afternoon? All right. So yes, as I mentioned, I am interested in studying in particular the impact of UV on characterizing exoplanets. And a lot of my research comes down to this question of, are we alone in the universe? I'm really interested in, can we detect life in the universe? And keep in mind, I'm not talking in this talk about intelligent life. I'm only talking about things like microbes, single-celled